Centralized search relies on massive physical infrastructure. Towering server farms process the billions of data streams flowing into a single central choke point. This map shows global data convergence. Even at fiber optic speeds, routing all queries through one physical location introduces queuing delays and physical distance latency. Latency is the time required for a data packet to travel from its source to its destination. Early peer-to-peer networks bypassed these hubs by linking nodes directly, but these systems lacked structure. A query would bounce randomly between nodes, creating severe multi-hop propagation delay that could take several seconds to resolve. This performance gap created a persistent engineering heuristic. Developers assumed they had to choose between high-speed centralized silos or slow, resilient decentralized networks. Modern architecture assumes that peer-to-peer systems must accept high latency as the price of user sovereignty. This perceived trade-off is mathematically unnecessary. Decentralized search indexes can achieve high speed without compromising on user sovereignty. Well-engineered local node architecture achieves sub-second query resolution, outpacing monolithic silos. Building this sovereign infrastructure requires three specific layers. First, Kademlia DHTs, the Libp2p transport framework, and gossip protocols. Deconstructing and engineering these pillars allows for high-speed peer discovery without a central masternode. The primary challenge for decentralized infrastructure is locating data in a vast network without a central index to provide the address. Kademlia distributed hash tables, or DHTs, solve this by replacing random searching with structured mathematical routing. A DHT is a decentralized storage system where nodes and data are mapped to specific coordinates. This diagram shows nodes across the globe. Kademlia ignores geographic distance, instead organizing nodes into a logical binary tree based on their proximity in the network's address space. To measure this proximity, Kademlia uses the XOR metric. XOR, or exclusive OR, is a bitwise operation that calculates the absolute logical distance between the searching node's ID and the target's ID. This calculation creates an O log n lookup path. O log n is a mathematical efficiency where the steps required to find a target grow slowly as the network expands. Each hop through the tree halves the remaining distance to the target. Targeted halving eliminates the blind broadcasting that caused heavy congestion in legacy networks. Kademlia provides the foundational logic for sub-second discovery by guaranteeing the most predictable path to any data point. Mathematical logic must still translate into physical communication across global hardware. Libp2p is the modular transport framework that executes Kademlia's routing logic. Libp2p manages peer identification and secures the communication lines between nodes. It creates secure, multiplexed channels that allow different hardware environments to talk to one another. This modularity ensures the logic layer functions even when packets encounter firewalls, network address translators, or different underlying protocols like TCP/IP and UDP. Libp2p acts as the physical bridge, turning abstract efficiency into a secure communication layer. Even with optimized routing, distributed systems face a final physical bottleneck, multi-hop propagation delay as updates move through the network. Moving data hop by hop takes time. Every physical mile and network switch adds milliseconds to the process. Blasting updates to every connection, known as network flooding, fails because it exhausts available bandwidth with redundant data. This bottleneck is cleared by implementing selective gossip protocols. In a gossip protocol, nodes selectively pass state updates to a small, calculated subset of our neighbors. This method ensures high availability, a system property where data is constantly accessible. Gossiping pre-propagates index states, so the information is already waiting locally when a query begins. It also ensures privacy. Data moves statelessly across sovereign nodes, meaning no central server logs the movement or contents of the update. Gossip protocols neutralize propagation delay by pre-warming data paths, delivering speed without sacrificing privacy. With these pillars in place, we can execute a sub-second search in a fully decentralized environment. When a query starts, Kademlia calculates the XOR path, while Libp2p secures the transport framework. Because of continuous gossiping, the target data is already highly available at a nearby node. The query resolves in a fraction of a second. The synergy of structured routing, secure transport, and preemptive gossip breaks the performance limits of legacy peer-to-peer systems. This architecture removes the need for centralized server farms to maintain high speeds. Local node architecture provides a performance upgrade over monolithic silos while maintaining system resilience. Sub-second, sovereign infrastructure demonstrates that true decentralization and high performance are no longer mutually exclusive.